All right, let's get started. So today we're going to talk about actor-critic algorithms, and if you're all in here, then I assume that means you finished your homework, and if you're watching this online about 12 hours from now, then I hope you've already turned in your homework. For those of you that are watching this online, the room is a little sparser, and I assume that's because you're all working very hard on your homework. All right, some logistical notes. So yes, homework 1 is due today, and hopefully everyone is in good shape with that. There will be the office hours this afternoon that the GSIs will be holding, and of course we'll be answering your questions on Piazza. So hopefully you're all in good shape with that, so please don't be late. Homework 2 will be out today. We'll try to get that out to you sometime this evening, so those of you that are really eager to get started at 12:01 a.m. on Tuesday, hopefully it'll be online for you by then. And actually, you should start early on this, and a lot of the material for homework 2 we've covered last week in the policy gradients lecture, and some last bits and pieces we'll finish up today in the actor-critic lecture. So homework 2 will be primarily about policy gradients. And then remember to start forming your final project groups. A few of you came into office hours to talk with me on Friday. That's great. Hopefully you guys are all starting to think about projects, starting to think about forming groups. Unfortunately, I won't have office hours this Friday because I have a deadline that I need to do my homework for, but next week I'll have office hours on Friday again, so please do come into the GSI office hours or come into my office hours if you have any questions about projects, or if you just want some help brainstorming, we're happy to do that. But yeah, do start thinking about that. Okay, today's lecture. We're going to talk about that's number 2. We're going to talk about improving the policy gradient with a critic. So the idea here will be, instead of just training a single neural network to be the policy, we'll actually introduce a second neural network that we train that's going to assist the policy to learn better. We're going to discuss what's called the policy evaluation problem, which is the problem of learning how well your policy is currently doing by training a critic, and I'll explain what that means. We'll talk about discount factors. This is how we can handle infinite horizon problems, which becomes more relevant in actor-critic settings. We'll discuss the actor-critic algorithm, and then a few other more advanced ideas for variance reduction. So the goals of today's lecture will be to understand how policy evaluation fits into policy gradients and understand how actor-critic algorithms work. So this is what we'll try to get through today. Okay, let's recap a little bit from last week. Let's just throw up a brief summary of policy gradients. So this is the reinforce algorithm that we learned about. The reinforce algorithm, in some ways, the simplest reinforcement learning algorithm you can have. It's basically gradient ascent or gradient descent if you have costs for reinforcement learning. And it consists of 3 steps. The first step is to sample trajectories from your policy. That means just run your policy on your robot or on your simulator. The second step is estimate your gradient. So in order to estimate your gradient, you sum together the rewards along your trajectories and you multiply them by the gradient of the log probability of the actions. And then you just increment your parameters by some multiple times the gradient. And in practice, you can use more advanced gradient optimizers like SGD with momentum, or ADAM, or ADAGRAD, and so on. In fact, in your homework, you'll be doing this using an optimizer called ADAM, which has an adaptive step size adjustment. And we talked about how policy gradient fits into this framework where you have 3 different parts to any RL algorithm. There's the sampling part, that's step 1. You have to fit a model or estimate your return. So there's no model being fitted, but there is a return being estimated by summing together the rewards. So that's this thing right here. And then you improve the policy by taking a gradient step. So estimating the return means sum together the rewards, and we refer to those as Q hat. And improve the policy means take a gradient ascent step. And this is the form of the estimator written out with samples. Okay, and I mentioned that this bit here, which is the sum of the rewards, you can refer to this as the reward to go. So if we exploit causality, we sum together only the rewards from the current time step until the end. That has a very natural interpretation. It's all the rewards that you'll obtain starting from that time step until the end of your episode. And this is the quantity that we're going to work with in today's lecture. We're going to talk about different ways that we can estimate that Q hat that might work a little bit better than just summing together the rewards. Okay, so let's dig into this a little bit more. So this Q hat is the estimate of the expected reward if we take an action A in state S. And the use of the letter Q here is not an accident. This is very closely related to Q functions. It's an estimate of this quantity, but it's a very particular estimate. It's an estimate that uses just a single sample. So can we get a better estimate? Let me explain what I mean by single sample. Let's say that you're at this, so this is a trajectory, right? And let's say that you're at this state and this time step. If you want to estimate the expected reward to go, and all you have is this trajectory, well, all you can do is you can sum together the rewards in this remaining little bit here. So you can sum together these rewards, and that gets you an estimate of the reward to go from that time step, but it's a single sample estimate. You might have some other trajectory over here, a different one, but that one doesn't visit the same exact state. So you can only use that one trajectory and its remaining states to sum together the rewards to get the expected reward to go. So that's this quantity. That's the sum from t prime equals t to capital T of the rewards along this little tail piece right here. The reality, of course, is that there are many possible futures that might result from this state, either because your policy randomly chooses a different action, or it might choose the same action, but the stochastic dynamics of the environment might lead it into different states. So the reality is that the true expected reward from that state is more complex. It's some expectation that depends on your policy and on your dynamics, and there are many possible futures, all of which need to be averaged together to obtain the true reward to go. So this sum right here is a single sample estimate of some true reward to go that can only be obtained by integrating over all possible trajectories emanating from that state at that time step. Does anybody have any questions about this? Okay, good. So there's a true expected reward to go that we do not know, but if we knew it, we could simply plug it in here, so we could replace this q hat with a true q if we had some way to evaluate this true integral, and this would be a better estimate of the reward to go. Better in the sense that this is the true thing, and this is a single sample estimate of that true thing. So if you have a single sample estimate of some expectation, that estimator has a high variance, because it's using just a single sample. If you have infinite samples, then you'll have lower variance. So that means that if we had some way to get the true expected reward to go, and we could plug that into our policy gradient, we would have a lower variance policy gradient. And as we discussed last week, variance is one of the biggest problems with policy gradient estimators. So if we have some way to reduce the variance, we would have a better estimate of the gradient, which would allow us to converge to a better solution, or use a larger learning rate, which would allow us to converge faster. So anything we can do to reduce the variance of the policy gradient will make it better. And if we had some way to get the true expected reward to go, that would make it much better. And in fact, we might choose to add a baseline as well. And for reasons that I'll discuss on the next slide, the value function, which is the expectation of the Q function under the action distribution, is actually a very good baseline. So let's dig into this a little bit more. So the Q function is your expected reward to go. We put that in there. And then we might want to subtract some baseline. And the baseline that we discussed last week is the average reward, right? So when we had these single sample estimates, we would just average together the rewards, and we would just subtract the average reward. We can actually have an average Q value as well. Now, the average Q value will actually depend on the state. So what do we average? Well, let's average these things, because that's the thing that we're subtracting from. So let's average together the Q values. And now, this has a very natural interpretation. So first of all, the average of the Q values is the value function. That's how it's defined, because these actions are sampled from our policy, right? So we can put the value function there. We have Q minus V. And this Q minus V is called the advantage, and we're going to use A to denote that. So let's just summarize these definitions. So we have the Q function, and I'm going to put a little superscript pi on it to just make it clear this is the Q function for the policy pi, for the current policy. Then we're going to improve that policy, and then we'll have a new Q function. We have the value function, which is the expectation under the actions drawn from the policy of the Q function. So at any given state or time step, the value function is the average Q function, because those samples are drawn from your policy, which means that this is actually the average Q. And then the Q function minus the value function tells us, for every action, how much better is that action than the average action, right? So because the value function tells us the expected reward of the average action from the policy, the difference between the Q function and the value function tells us how much better is this action than the average action. And that's why we call it the advantage. It's how advantageous that action is compared to the typical action drawn from your policy. And of course, because of how V is defined, if you average together the advantages over the actions drawn from the policy, that averages out to 0, right? Because that's where we're getting the V. We get the V by averaging together the actions, so if we average together the difference, we get 0. So the average advantage is 0, and for any given action, its advantage tells us how much better it is than average, which is exactly what we want. We want to take the actions that are better than average, make them more probable, take the actions that are worse than average, and make them less probable. So that's why if we want a good policy gradient, we'll just substitute in directly the advantage. This is the real expected advantage of an action over the typical action drawn from the policy. And the better we can estimate the advantage, the lower the variance of the policy gradient will be. So at a very high level, pretty much the entirety of today's lecture is concerned with getting a superscript pi. Because the better we can do at getting a superscript pi, the better our policy gradient will be. OK, so this is the estimator that we saw last week. Sum together the reward and subtract the baseline. This estimator is unbiased, meaning that in expectation, it'll be the correct gradient of the policy. But because this is averaging over a single sample, it can have high variance. So most of what we'll do today is we'll actually use some kind of neural net in here, which will introduce bias, because the neural net won't be perfect, but it will greatly reduce the variance of the policy gradient. Because policy gradients tend to suffer from high variance, oftentimes introducing a little bit of bias for the sake of reducing the variance is a good trade-off. OK, does anybody have any questions about advantage functions, Q functions, or value functions that we discussed here? Yes?
Is this the same Q function as in Q learning?
It is a little bit different. So we'll actually talk about Q learning on Wednesday. And the main difference, which we'll discuss more on Wednesday, is that you can have a Q function for a particular policy, which is what this is, but you can also have the optimal Q function, the Q function for the optimal policy. And that's actually what is being learned in Q learning. So there's a little difference. Both are expected rewards to go, just under a different policy. Any other questions? OK. So the actor-critic algorithm is going to also fit into the scheme with three different parts. The sampling stage will be the same. You'll run your policy in the simulation or on your real system. The fitting a model, so the policy improvement step will also be the same. We'll still take a gradient step. But the fitting the model step will now involve actually somehow estimating Q pi, V pi, or A pi so that we have a better gradient. So we won't change this thing, but we will make some changes up here to get a better estimate of the advantage. So that's mostly what we'll be doing. All right, so let's talk about fitting value functions. So the question that we have to ask first is, what are we going to fit, and what are we going to fit it to? So there are three objects that I've introduced, Q pi, V pi, and A pi. All of them are very closely related, but we have to choose which one we're going to fit. So one natural thing we might say is, well, let's just fit A pi, because that's the thing that we're going to have in here. Let's generate some data. Let's run your favorite supervised learning regression to fit a neural network to advantages, and let's do that. But there's a little trick we can do. So the thing about A pi is that it depends on two things. It depends on states and actions. And the more inputs you have, the more parameters you need, the higher the variance will be. But there's a very close relationship between Q values and value function values. So this is the Q function. It's the sum of the expected rewards. And you can write out the Q function like this. You can say that it's the first reward plus the sum of future rewards. And we covered this earlier on in the lecture when we first introduced Q functions. And this thing is not an expectation, because when you give the Q function a state and action as an argument, that fully determines the first reward. So the first reward is not actually stochastic. It's completely determined. But after that, you get expectations. So when I've written it out like this, I didn't lose anything. This is still completely correct. This piece right here, this is the expectation of the value of the state at the next time step. Now, this thing is an expectation, because if your dynamics are stochastic, you might get different states at the next time step. However, so this is the true statement here. So it's an expectation right here. But if we're willing to make a little bit of an approximation, if we say, let's just use a single sample estimate, not for the whole trajectory, but just for the next state, then we can just plug in the value of the next state that we saw along that trajectory. Now, here we have lost something. We've gone from the full expectation over the next state to a single sample estimate, but it's just for one time step. So if you remember that picture with the different trajectories going out, we've just sampled the first one, but the rest is still being integrated. So we've lost a little bit, but not very much. What we've gained, however, is that we no longer will need to learn a function of both s and a. It's going to be enough for us to just learn v, which is a function of only s. So in particular, the advantage is the Q function minus the value function, so we can substitute this equation in here, and it's r plus next v minus current v, and that's super convenient. So let's just fit v pi, because if we fit v pi, then we could just plug it into this formula and get a pretty good estimate for the advantage. Not quite as good as if we fit the advantages or the Q values directly, but very, very close, because it's only one time step that we're losing. And this is a function of only the state, and it doesn't depend on the action anymore. So there's a much smaller space for it to deal with. So most actor-critic algorithms will actually fit just the value function, because it's so convenient and simple, and you can recover the advantage just by plugging it into this formula. You can have an actor-critic algorithm that fits a Q function as well, but it's a lot less common. OK. Does anybody have any questions about this slide? All right. So just to make this concrete, what we're going to do is we're going to have a neural network. That neural network is going to take in the state, and it's going to output an estimate of the value function. So now I'm going to put a hat on the v, so it's now v hat pi. And that neural network is going to have some other parameters. I'm going to note these parameters as phi, so as not to confuse with the policy, which has parameters theta. So we're going to learn this v hat superscript pi subscript phi, and we're going to train it to be an accurate estimator of the value function of the current policy pi. So the process of fitting this value function to a given policy is sometimes referred to as policy evaluation, because this step is not trying to improve the policy, it's just trying to figure out how good is the policy from any given state, hence policy evaluation. So again, this is the value function. It's the expectation of rewards that we get if we start in a particular state. Our new diagram for the algorithm, the only change now is that the green box is just going to fit v pi, because we know that once we have v pi, we can recover the advantage. One of the nice things is that the overall objective of reinforcement learning at j theta, that's just the expectation of the value function in the first state. So if we fit the value function, we've also estimated the overall performance of our algorithm. That's good. So how can we perform this policy evaluation? So there are a few options that we have. One of the options, this is sometimes referred to as Monte Carlo policy evaluation, and that's what policy gradient does. That's to just roll out your policy and sum together the rewards. So you can say, well, let's make our v pi just approximate these sums. So that means that you take your trajectory, you roll it out, and at every state, you add together the remaining rewards. Now, you might say, OK, why is this useful? It seems like you were adding together the rewards before, you're adding together the rewards now. What have you actually gained? Well, one of the things that you might gain here is that this v is now going to be some function approximator, for example, a neural net. And that function approximator is going to average together the returns along different trajectories. So you could, for example, just say, OK, let's do what policy gradient does and actually sum together the different rewards. This would require us to be able to reset the simulator back into the state and actually do these rollouts. But with a function approximator, you can do a little bit better. So here's our, now we're going to have this v hat. It's going to be a neural net. And we roll out our trajectories. But we don't have just one, of course. We have some second one over here. This one is not from the same state, so it doesn't visit exactly the same states as you go along this other trajectory. But because this is a neural network, it's going to figure out that when you input two very similar states, it's going to produce two relatively similar outputs. So that means that the same function should actually fit multiple samples, and in the process of learning to fit multiple samples, it'll average together those returns. It'll actually get you potentially a lower variance estimator. So if you got, for example, really lucky over here, and you got really unlucky over here, the function approximator will look at these two things and say, well, this doesn't make sense. These two states are very, very similar, but this one is really good and this one's really bad, so maybe I'll average out their returns a little bit and get a slower variance. So the more samples you add, the better this function approximator will be at actually averaging those out and getting you things that look more like the real solution. Now that will introduce bias. Maybe there really is a cliff between these two states, and this one really is very good and this one really is very bad. So perhaps that won't actually be the right answer, but it will certainly be lower in variance. So it's not as good as actually resetting your simulator like I had on this previous slide and doing multiple rollouts. So if you could actually reset this and just try multiple trajectories and average them together, that would be better. But it is going to reduce your variance. So it's still going to be pretty good. So let's just make concrete what it is that we're doing here. Training this v hat is a supervised regression problem. In order to formulate it as a supervised regression problem, we need to collect training data. And the way that we collect training data is by running our policy. And when we run our policy, every state that we encounter along every trajectory, that's over here, SIT, and the label for that state is the sum of the rewards from that state until the end along that trajectory. That's the reward to go. And I'm going to denote these labels as Y subscript I comma T, so Y is the target for regression. So I'm sometimes going to colloquially refer to these as target values. So you collect your data set that consists of states and Ys. And Ys are just, in this case, reward to goes. They're just sums of rewards. And then you just solve a supervised regression problem. So we're just going to take the output of this neural net and we'll minimize the squared difference between this output and the target values. Why squared error? Well, part of the reason is because it's pretty simple. It's a very common loss function to use for regression. But actually, later on in the course, when we talk about stochastic optimal control, we'll actually find that using squared error for regressing onto target values actually has a very interesting probabilistic interpretation that actually makes some sense in the context of optimal control. But for now, let's just say that we're doing regular regression, and squared error is a very popular loss function to use for regression. Actually, there are a few other choices you could use other than squared error. So those of you that are familiar with a Huber loss, it looks a little bit like a absolute value function with a little smoothing at the bottom. That also works pretty well for these kinds of problems. Yes?
So since this value function depends on your policy, does that mean that you have to do this regression problem during test time?
That's right, yeah. So not during test time, but because at test time you're just running your policy. But you do have to do it within every iteration at training time. And I'll show pseudocode of an actor-critic algorithm later that'll make this apparent. The short version is that you can warm start your network. Any other questions about this? OK. All right, so can we do better? So far, I talked about how we can regress onto these Monte Carlo estimates of the reward to go. And I talked about how that is a bit better than just directly plugging those sums into your policy gradient, because the function approximator is going to average over different states. But maybe we can do a little bit better. Maybe we can lower our variance even more. So one of the things that it helps to think about, if we want to think about how we can do better, is what's the ideal target value? What's the perfect target value that if we knew it, that would be as good as anything else? Well, the perfect target value is the actual expected reward. That's sort of, in some ways, an obvious answer. We're trying to estimate the value function. So if someone told us exactly what the value function was, that would be the perfect target value. We don't have that. So what we have is we have this Monte Carlo target, which, again, is a single sample estimator. But we can do the same trick here that we did with the Q function. We can say that this expectation, we can expand it recursively. We can say that it's approximately equal to the reward at the current time step plus the next expectation. It's approximate because there is an expectation here over the A's, so we've sort of approximated that with a single sample. And this second part, this is just the value function. So this is approximately equal to the current reward plus the next value. And now we can do a little trick. This is sometimes referred to as the bootstrap. We can take our neural network, which is an approximation of the true value function, and we can plug it in there. Now, if the neural network is a better approximation to the value function that's summing together the rewards, which we really hope it is, because otherwise we should just be using sums of rewards, if it's a better estimator, then plugging it in there should give us a better estimate of the target values also. One way you can think about this is that you're sort of using your data one time step at a time. So it doesn't really make sense to regress directly to the outputs of your function approximator, because then you're sort of, you're not actually doing anything, you're just asking it to copy itself. But if you give it one step of the reward function, then put in the function approximator, now you're giving it a little bit of knowledge from the environment, a little bit of that data, but still reducing the variance by putting your function approximator right on the next step. So this is sometimes referred to as the bootstrap. This is a very common principle in reinforcement learning. So we can directly use our previous fitted value function and just plug it in for the second time step. We can also plug it in for the third time step or the fourth time step and so on. This is sometimes referred to as n-step returns, where you sum together the rewards for n steps and then put in the value function. And we'll come back to that later in the lecture. So in this setup, your training data now, again, it has the state that you encountered along your trajectory, but now instead of summing together all the rewards from that step until the end, you're going to take just the reward you saw at that time step and add to it the value function at the next time step. And then you'll add these together. And that will get you more bias, because this thing might be incorrect, but it'll get you lower variance typically, because this v hat hopefully does a better job of estimating the full expectation than just a single sample estimator. And again, these are our target values y. So then we again do our supervised regression onto the y's. This part hasn't changed at all. All we've changed is the labels. And this is sometimes referred to as the bootstrapped estimate. This is actually by far the most popular way of doing this, by the way. Does anybody have any questions about this approach? Yes?
So how do you do the first step?
Right, how do you do the first step? This is kind of worth thinking about. Let's imagine that you initialize your network such that its outputs are pretty small. One way to do this is to have the last linear layer of weights be 0 or some small randomly sampled value. Then when you compute these target values, they'll pretty much just be equal to r. Okay? So when you do the first step of this, the value function will sort of learn the first step rewards. So then, when you go around again and you put the value function as the target, now you get reward plus something that looks like a reward. So now you have 2 steps of rewards. And then you turn the crank and do this over and over again until eventually the value function has all of the rewards. So one of the things to remember about this is that in contrast to the Monte Carlo approach on the previous slide, here you do have to retrain your function approximator multiple times before it gets a good value function estimate. And how many times depends on your horizon, or perhaps on your discount factor, which I'll talk about in a few slides. Okay, any other questions about this? Yes?
Does it matter if we have an optimistic versus pessimistic, like initialization of the reward?
You mean of the value function?
Excuse me.
Yeah, so it doesn't matter if we have an optimistic or pessimistic initialization of the value function. So generally, it will affect the convergence properties of the algorithm, depending on how many iterations you run it for. There are actually some maybe a little more relevant when we talk about Q-learning on Wednesday, but there are actually some exploration heuristics that intentionally initialize value functions to be very large to encourage policies to sort of prefer areas where they haven't been, because if they're sort of large everywhere they haven't been, then you'll think the places you haven't been are actually good and you'll be incentivized to explore. In general, for actor-critic methods with neural nets, oftentimes we initialize the value function to have fairly small outputs for the sake of stability. Yes?
Can you also target like upper confidence bounds?
Yes, so there are actually value function fitting algorithms that reason about confidence bounds. I believe that Aviv Tamar might talk about this towards the end of the course. He's going to have a guest lecture and he might talk about risk-sensitive reinforcement learning there. Okay. So all this stuff that I discussed, this is sometimes referred to as policy evaluation. It's not trying to change the policy, it's just trying to estimate how good is your policy right now in various states. And policy evaluation, in some cases, actually has a very natural interpretation. So these value functions might seem a little bit abstract. It's like the sum of rewards over all time and its expectations. But depending on the form of your reward function, these things might have a very natural interpretation. So one very classic example I guess what we would today call deep reinforcement learning, this is actually from 1992, using neural networks for reinforcement learning, is this thing called TD Gammon by Jerry DeSaro. This is a very famous backgammon playing algorithm that uses value function learning. It's not actually actor-critic, but it is learning value functions. And in this system, the value function is looking at the state of the board, and it's trying to estimate the value for a reward function, and the reward function is the game outcome. So in backgammon, there are actually 5 outcomes, but there's only 4 that are considered. So there's a 5th outcome that's extremely rare, but the 4 outcomes considered here are one of the players wins, the other wins, a draw, or a gammon. So there's 4 possible outcomes, and the value function is actually just the expected outcome given the current board state. So policy evaluation here has a very natural interpretation. You look at the board, and you make your prediction about who's going to win. That's actually quite semantically meaningful, and you could just look at the numbers for this thing and figure out what it's essentially what it's thinking. A much more recent example of essentially the same thing, AlphaGo, which is a Go playing program that uses a combination of Monte Carlo tree search, value function fitting, and policy gradients. Same deal. The reward is the outcome of the game, who wins and who loses, and the value function is a convolutional neural network in this case that looks at the board and it tells you who it thinks is going to win based on the current configuration of the board. So policy evaluation in some cases might actually have a very natural, very intuitive interpretation. Okay, so now that we've discussed policy evaluation, let's put the pieces back together put that back into policy gradient, and go through an example of an actor-critic algorithm. So this is what is sometimes called a batch actor-critic algorithm. I'll talk about online actor-critic algorithms afterwards. That's the other type. And these are kind of policy gradient with value function approximation. So it's sort of the closest thing in the phylogenetic tree of our algorithms to policy gradient. So step one, just like in reinforce, we run our policy on our system, on our physical system, on our simulator, on our autonomous car, whatever it is that we're training, and we collect sampled states, actions, and also rewards, actually. Then we fit our neural network critic, our v hat superscript pi subscript phi, by training it on the sampled reward sums using one of the two policy evaluation methods that I mentioned on the preceding slides. Then we evaluate the advantage at every single state and action that we've seen along all of those sample trajectories. And we evaluate the advantage just using this equation. So it's very, very simple. We just take that reward plus the next value minus the current value, where we've already trained this v hat. And then we just plug these advantages into the policy gradient on step 4. So this is exactly like the policy gradient in reinforce, except that this thing, instead of being a sum of rewards, it's these a hat values. And then we, again, take a gradient step on theta. So our v pi is this expected reward. We can have different choices for how to fit the v pi. We can do the Monte Carlo thing. We can do the bootstrap thing. So those are all choices that we have. So the bootstrap thing is a bit more common in practice. OK. Does anybody have any questions about the batch actor-critic algorithm? Yes?
So just to clarify, after the second, if you're using bootstrapping, after the second time step, you wouldn't be predicting the full rollout, but just the next time step with the approximation from the previous V?
The second step, you mean number 2 here, or you mean second step?
Like after the second loop, then number 2 would turn into...
So number 2 here is it's sort of an abstraction. Number 2 is fit v hat. How you fit v hat is kind of up to you. So a very heavyweight kind of batch mode way of fitting v hat is actually do multiple rounds of this retraining. So fit v hat might mean set your target values based on your current v hat, run the regression, set your target values again, run the regression, repeat this like n times. And that could all be happening within step number 2 if you want really, really accurate estimates. You could also do something a little cruder. If you're more concerned about going fast, you might say, OK, well, let's just go around once in step 2. Let's just update our value function once based on the previous value. And that's not going to be totally accurate, but it's pretty quick, and it might be good enough. So that's kind of a design choice. In fact, we'll see many of these algorithms. We'll see this also on Wednesday when we talk about fit a Q iteration, that there's all these algorithms that have kind of an inner loop. And how many times you go around the inner loop is kind of a design choice. It affects stability, it affects convergence, it affects computation time. Yes?
How does, I guess, if we do a bootstrapping kind of thing, how does v hat learn that it's supposed to be looking at all the future rewards instead of just the, I guess, the current reward?
Well, it's because of how it's trained. So it's trained to target the current reward plus the next value. So every time, so if you start off with v's being approximately 0, every time you go around and retrain it, the v's will increase.
Okay.
In fact, this is actually what I was going to discuss on the next slide. They'll continue to increase, and the way that I've written it here, they'll actually increase without bound, which is a little bit disturbing. There's a little fix for this. So yeah, they'll continue to increase. So what if the length of the episode goes to infinity? Actually, the way I've written it, even if it doesn't go to infinity, you're kind of in trouble here. But if there's something in the state that tells you, are you close to the end or not, it can kind of figure out where you are. But sometimes your episodes might be infinity, in which case you're just in trouble. These values will increase without bound. Now, sometimes having finite length episodes might make a lot of sense. So if this little robot is learning how to stack a Lego block, its existence consists of these discrete episodes. So it exists for 5 seconds, then the world resets and it tries again. So here it makes sense to have a finite t. But if you have like this little guy learning to run, you probably want him to run for a really long time. So there it might make a lot of sense to say I want infinitely long episodes. I don't really care about his ability to run for 5 seconds. I care about his ability to enter a cyclical periodic gate that allows him to run perpetually. So in many cases in RL, you might actually want to consider infinite or approximately infinite episodes, in which case this way of writing the target value is really, really problematic because these values will just continue to get bigger and bigger and bigger. So there's a way that we can address this issue. That's called a discount factor. The discount factor at first comes off as a little bit of a heuristic, but it actually has a very natural probabilistic interpretation. So here's the intuition behind the discount factor. If you tell me that you're going to give me $2 million, I'll be probably pretty happy. But if you then tell me that you're going to give me $2 million 200 years from now, I might still be kind of happy. You know, maybe my descendants will benefit from that, but not quite as happy. You know, so something about that 200 years kind of makes that $2 million less valuable to me. And if you tell me that I'll get it in 2,000 years, then I won't care at all because, you know, who the heck knows what's going to happen in 2,000 years and whether we'll be using dollars or not. So somehow, that even though that number of years doesn't seem to have anything to do with the number of dollars, it strongly affects the value of that money to me. And reinforcement learning might be the same way. You know, maybe this little running guy, maybe he would rather get his reward now rather than 200 years from now. So the discount factor is essentially a formalization of this. It says that we prefer rewards to happen closer to today, to happen sooner, than to happen later. And the way that we do this is by introducing a little number in front of this v called gamma. It's always called gamma for some reason. And that number is between 0 and 1. The 0.99 works pretty well. So it's a number that's pretty close to 1, but not exactly 1. So that each time you back up one step, your value decays a little bit. You can think of this as like inflation. You know, if you have money in the bank, there's some inflation, and every year, even though the number is the same, it's worth a little bit less. So this is adding a little bit of inflation to your rewards. So money later, reward later, is worth less than reward now. So what's the mathematical interpretation of this? How does this gamma fit into the framework of MDPs? Well, it turns out that using gamma doesn't actually change the MDP framework. It just changes your transition function a little bit. So here's how gamma changes the MDP. Let's say that I have this very simple discrete Markov decision process with 4 states. And I can transition between those states with some probability p of s prime given s comma a. When I introduce a discount factor, what that does is it adds a death state. It says that with probability of 1 minus gamma, every single time step, I might die. And if I die, I collect no rewards. This is a very kind of atheist view of existence. So if you die, you get no rewards. And then it makes perfect sense that you put the gamma up here, because what this equation is really saying, the next value is gamma times v plus 1 minus gamma times 0. Because if you die, your value is 0. You never collect any rewards. And that's what that gamma is really doing. It's just that expectation all over again, and there's a missing ghost term here, ghost because you're dead, which is 1 minus gamma times 0. And that means that these other transitions, they're still there, except that now they're whatever they were before times gamma. So discount factors means you prefer to get your rewards sooner rather than later, for the same reason that human beings do, which is that someday you will die, so you'd rather get your rewards before you die. Very simple, very natural, yes?
So why does it make sense to set gamma as a fixed value rather than a learned value? Because it seems like a probability that's not fixed for dying.
Well, so gamma is a parameter of the problem. So you set up your problem and you say, the reason that I prefer rewards sooner rather than later is because every time step there's this probability of 1 minus gamma of transitioning to the absorbing state. So this is something that's designed. If you were to try to optimize gamma and your rewards are mostly positive, you would probably just want to set it to 1 because you'd rather collect those rewards. So there'll be a degenerate solution. So gamma is not a property of the network. It's not a property of the critic. It is a property of the problem statement. It is a property of this Markov decision problem that we're solving. And specifically, it's a property actually of its dynamics. So in the same way that you don't choose the dynamics, you don't choose the gamma. Any other questions? OK. So now, let's talk a little bit about how discount factors fit into policy gradients. And here, the story will get a little bit more complicated. So the discount factor has this very natural interpretation as a modification of your transition dynamics. But the way that it's actually used in policy gradient sort of makes the story a little bit more complicated. So what about Monte Carlo policy gradients? Let's forget about the critic for now. Let's just try to plug this gamma into the policy gradients that we learned about last week just to understand them better, and then we'll bring things back into actor critic land. So there are 2 ways that we can introduce a discount factor into policy gradients. And the same 2 ways actually apply for actor critic, but I'll just write them out in regular policy gradient notation. So option 1, let's take our reward to go, and let's put the gamma in there. Very natural. So this just says that the reward at time step t is multiplied by 1 because this is gamma to the 0, plus the next reward times gamma, plus the next reward times gamma squared, and so on and so on and so on. This all makes reasonable sense. And then option 2, let's go back to the policy gradient that is not temporally decomposed, the one that doesn't exploit causality, and let's put the gamma in front of that. Now, this again is very natural. You're saying, okay, you have some trajectory. You're going to sum together the rewards along that trajectory, and now you'll discount those rewards by gamma to the t minus 1 power. So the second time step will get a gamma, the third one will get a gamma squared, and so on and so on. And then we'll just multiply that sum by the sum of the policy gradients. That we also know is a reasonable thing to do for reinforce. And we can write down a temporally decomposed version of this estimator, and it's no longer going to be the same. It's also worth noting here that if you do have the critic and you plug in the gamma, this one looks a lot like this one, right? So if you have the gamma in here, that's the same as putting the gammas within the sum there. But so these and these are the same, but these and these are actually not the same. And here's why. Let's take this estimator, the option 2 estimator, and write down its temporally decomposed version. OK, so we distribute the sum. And now we have gamma to the t prime minus 1. OK, this is a 1, and this is a t, so that's not the same. So that, what we can do is we can actually take the additional gamma terms, and we can take them out of here and put them in front of here. This is just mathematically equivalent. And now I have gamma to the t minus 1 in front of the grad log pi, and then gamma to the t prime minus t in front of here, just like up there. So this and this are both advantages, but this now has this gamma to the t minus 1. What does that mean? Well, it means that later steps matter less. Right? That makes sense. If you're starting off at time step 1, then later time steps matter less to you because you care about more recent rewards. But something is a little weird here because we started with the correct policy gradient estimator. We crunched through all the causality stuff, and we ended up with something that looks almost the same as the actual critic version in that we have discounted here, but now we're also discounting the gradients for some reason. Discounting the gradients is actually the correct thing to do. That's the correct thing to do if you want to optimize the discounted return from time step 1. So in the interpretation of gamma minus 1 minus gamma is your probability of dying, this is actually the right thing to be doing. But almost nobody actually ever does this because it's not actually what we often want. So again, these are the two options. They only differ by whether or not we include the gamma in front of the gradients, which is to say we think that the gradients at later time steps matter less. This option 2 is the right thing to do under this absorbing state interpretation. So that's correct. Later steps don't matter if you're dead, so we should discount their gradient. But this is the one that we actually use. This is the one that we typically use both in policy gradient and in actor critic algorithms. And when you implement discounting for your homework, for homework 2, you'll actually be implementing this version. And it kind of makes sense. So why do we use it? Well, if we want this guy to run for an infinitely long time, it kind of makes sense that we would consider gradients at later time steps the same way as gradients at earlier time steps, because we don't care that he's going to run fast at time step 1. We want him to run fast at all time steps. So something about this, the option 1, kind of flies in the face of this very neat absorbing state interpretation. And in fact, what we're really doing when we use this option 1 formulation is we're actually approximating average reward. So if you remember from the discussion of the definition of the RL objective, I talked about how in the infinite horizon, you can formulate an average reward, where you do 1 over capital T times the sum of rewards, and that is no longer an infinite sum because as t increases, the sum increases, but also the denominator increases. So deriving why this is an approximation to average reward is actually fairly complex, so I'm not going to go into it in this lecture. But if you're interested in this, there's a very nice paper by Philip Thomas called Bias in Natural Actor Critic Algorithms that discusses how when we do this, option 1, which is what we typically do, the right interpretation of this is that we're actually doing average reward and just using discount as an approximation. OK, so hopefully this doesn't completely confuse everybody, but there's kind of these two interpretations of discount. One is that you might die someday, so you should collect your reward sooner. But the other one, the one up here, is that it's an approximation to average reward, so that we can have finitely sized sums. OK, any questions about this? All right. So now let's take that discount and let's plug that into the actor critic. So the only thing I've changed is I put a little gamma in here. Now the nice thing with that gamma is that even if we have infinitely long episodes, things will still converge, things will still be finite. And we can actually now derive an online actor-critic algorithm. So the policy gradient algorithm and this actor-critic algorithm, they're batch in the sense that you generate multiple trajectories from your policy, and then you do some computation on a big batch of trajectories, you update your policy, and then you generate more trajectories. But with the actor-critic, you can actually have an online algorithm, which means that every time you take a step in the environment, you actually immediately improve your critic and your policy. So here's how it works. Step one, very similar to the old step one, except that now, instead of generating multiple trajectories in a big batch of data, we're just going to take one step. And we're going to get one new S, comma A, comma S prime, which is the next step we saw after we took that action, comma R. So we just take one step, we record the state, the action, the new state that we get, and the reward that we got for that step. Number two, we're going to update our critic, our function approximator, with one sample, and the target is going to be the reward that we saw plus gamma times the next V. And now you can see why we needed to go all the way to actor critic to get an online algorithm, because if we didn't have a critic, then we would have no idea what this next value is. But because we have a critic, and because we know how to do a bootstrapped estimator, we can just put that V in there without knowing anything about what happens in the future. Step three, evaluate the advantage. And this is just the advantage for that one state that we observed. Step four, compute your gradient. And this is a single sample gradient. And step five, take one step of gradient ascent to improve your actor. And then repeat. So this is the online actor-critic algorithm. OK, so at this point, well, first, does anybody have any questions about this online actor-critic algorithm? Yes?
Does that have a ton of variance?
Yes, it has a ton of variance, and I'll talk about how to get rid of that after the break. Any other questions? OK, let's take a 3-minute break, and then when we come back, we'll talk about some more advanced topics. Yes? Sure, yeah.
I guess we were talking about the examples, like the backgammon one and the go and AlphaGo. Like, for those choices of reward functions, I guess the, I mean, not reward, the value function, it makes sense, you know, like it's, I guess 0 if you lose, 1 if you win kind of thing. But would it, is the training going to be, like, I guess, sensitive to if you decide to scale it? I mean, like we were talking with policy gradient, it's like if you scale it, it's like, so actually it's 0 if you lose, and 10,000 if you win, or
oh, I see what you're saying.
minus if you won, minus 1 if you lose, 1 if
So
you win.
conceptually, it's OK. There's not much of a difference. In practice, there's a little bit of a difference because depending on how you're training your critic. So if you train your critic with, let's say, standard stochastic gradient descent, then scaling up the rewards basically amounts to scaling up the losses, which increases the magnitude of the gradient, so it's actually equivalent to increasing your learning rate.
Okay.
If you use an adaptive learning rate method like Atom, that will actually divide by the magnitude of the gradient, so there it actually will make no difference.
Okay.
Mathematically, it'll make no difference because the gradients will actually look exactly the same.
Right, for it. Okay.
Yeah.
What about like some sort of like I guess could you, I was thinking, you know, like if you could like sort of transform it, like instead of, I don't know, I guess a regular, I don't know, what's the word, like smooth it out from 0 to 1? To
Yeah.
So,
Yeah, I see what you're saying. There are two things that are kind of related to what you're talking about. So one is this thing called reward shaping.
yeah.
And I alluded to that a little bit when I talked about just the examples of the rewards for walking and reaching earlier in the class. But there's actually some more formal literature about what reward shaping really is. So if you're interested in this, there's a very well-known paper by Andrew Ng on reward shaping that describes sort of the math behind it and when it's OK and when it's not OK. So that's probably the main, yeah, I would say that's probably the main reference to check out if you're interested in that.
All right. Thanks.
OK, let's continue. So now that I've introduced the actor-critic algorithm, the batch mode, and the online actor-critic algorithm, there are a few implementation details I want to discuss, and then I'll also talk a little bit more about policy gradients and baselines and how critics can fit into that. So first, let's talk about some points about neural network architectures. So if we have something like an actor-critic algorithm, whether it's batch or online, we have now two function approximators. We have the policy pi theta and the value function v phi. So a very natural way to actually implement this, if we want to do deep reinforcement learning, is to have two separate neural networks. One of the neural networks with parameters phi that takes in the state s and outputs a scalar value, and one neural network with parameters theta that takes in the state s and outputs a distribution over actions. And again, that distribution over actions can be represented the same way as before. If it's discrete, then it's a big softmax. If it's continuous, maybe it's a Gaussian or a mixture of Gaussians or something like that. So these might be two completely separate networks. The advantage of this approach is that it's relatively simple and it's pretty stable. So oftentimes, if you're starting off with actor-critic, I'd recommend starting with this because it's simple and stable to get to work. But there aren't any shared features between the actor and the critic. And this can become a bigger deal if, for example, your states are extremely high dimensional. So if you're, for example, learning on top of raw image pixels, there's probably some low-level image features that would be really nice to share between the actor and the critic. So an alternative architecture is to have a shared network that has two outputs at the end, one scalar valued output for the value, and one output that gives the parameters of the distribution, either the softmax or the parameters of the Gaussian. This kind of network has the benefit of, I guess I don't have the pros and cons here. It has the benefit that you can now share the features between the actor and the critic, which is quite nice, especially if you have very large networks. You'll have fewer parameters. But it can be a bit tougher to get these architectures to train because they have two very different gradients being pushed through the shared parameters. So they have the policy gradients up here and the regression gradients up here. And these two gradients, they're essentially in different units. They're like different data types. So for that reason, it can actually be a little tougher to stabilize the training. You might need to be a little more careful with experimenting with weights or learning rates, including, as well as things like the network initialization and so on. So this is sort of a more efficient design in the sense that it shares features. And in principle, you could learn faster if, for example, it's easier to infer the right features from the actor signal that can then be repurposed by the critic. But it's a little harder to stabilize. So what I would say is that if you're developing your algorithm on top of a fairly fast simulator, like Mujoko or Atari games or something, start with this design first, because this design might be less efficient, it might take longer to train, but it's a lot easier to set up, and it takes usually less tuning to get it to work. But this kind of thing might be kind of neat at the end. And of course, it's up to you how much you actually have in these two heads, like whether this is just one fully connected layer for each of them, or maybe there's multiple layers in this arrow and multiple layers in this arrow. That's sort of a design choice. So two possible designs for the architecture. The two architecture design is simpler, usually easier to get to work. This one might be a bit more efficient. Yes? Oh, you actually just add them together, which corresponds to just sending these gradients through the network via this path and sending these gradients through the network via this path. So you can either add together the gradients or add together the loss and then compute its gradients. All right. Online actor-critic in practice. So right before the break, there was a question about, OK, in this online actor-critic, you're taking this gradient step with just a single sample, and you're updating this v hat with just a single sample. Those of you that are familiar with stochastic gradient descent for training neural nets, this would raise some red flags for you because training with a single sample is kind of tough because the variance is very high. And I've already complained in the past that this gradient has high variance, so this is going to do you no favors. In practice, if you want to use online actor-critic with deep neural networks, it's often a really good idea to have some way to construct a batch of size more than one. There's a little bit of a problem, though, because this is still an on-policy algorithm. So if you want it to be online, you need to construct a batch of size more than one on policy. On policy means that every time the policy changes in step 5 over here, all of your data needs to be thrown out. So somehow you need to either update your policy less often, which you can do. You can make the algorithm sort of quasi-online, which means instead of taking one step up here, you take multiple steps. Maybe you take like 5 steps, and then you do the update. Or a better way to do it is to actually train in parallel. So if you're lucky enough to be able to train multiple workers collecting samples, that tends to work pretty well with this algorithm. So This thing works best with a batch, as does this thing. So what we can do is we can have a parallel actor-critic algorithm. Now this requires us to introduce an additional assumption, which is that we can actually collect samples in step 1 over there from multiple independent workers, which is fine to do in simulation. That just means you spawn off multiple threads. But doing that in the physical world, if you're like driving a car, that means that you have more than one car. If you have a real robot, that means you have more than one robot. If you're doing, if you're regulating fans in a data center for energy efficiency, that means you have more than one data center. So after a while, this might get a little prohibitive. But we can go through and discuss how we might do this. So a simple way to implement your parallel actor-critic is to have what I'm calling here a synchronized parallel actor-critic. So that means that time goes down in this picture. You have some threads. In this case, there are 4 threads. And the blue boxes mean that they're stepping your simulator. So these 4 threads, altogether, they each take 1 step. And each of the 4 threads produces one S, A, S prime, R, and there's 4 of them. So you have 4 samples. Then each of these 4 threads is going to compute the gradients. And those gradients are going to get added together, and they're going to be used to update your thetas. So this is a synchronization point. So this effectively gets you a batch size of 4. And then you tell the threads, OK, you're done updating the gradients, take your latest theta, and keep going. And then they'll generate another data point, compute the gradients, and so on. And each of these steps, they're taken in parallel. Maybe if there's stochastic dynamics or with your stochastic policy, they actually end up taking different actions and going to different states, which is what gets you that diversity. And they're completely decorrelated, so that's good too. So you might even have these threads sort of, if your episodes are not fixed length, you might have them end at different points and restart. So this one might end an episode here and start a new episode over here. So they're completely decorrelated, which is nice because in stochastic gradient descent, you assume that your batch is decorrelated. This is a very simple way to implement parallel actor-critic. There's a more advanced way, and we'll actually have a longer lecture on parallel RL algorithms later in the course, but a short preview of that is that you can basically remove the synchronization point and use the sort of hope for the best approach, where every time one of these guys is finished with a step, they update they compute the gradients, they send those gradients to a central parameter server. That central parameter server accumulates gradients for a certain number of steps, updates the parameters, and sends out new parameters to each of the other threads as soon as they're ready. So this guy over here might still be taking a step with some old parameters, whereas there's new parameters available for the server, and you sort of like close your eyes and hope that this is not too terrible. Actually, it tends to work fairly well. So the removal of the synchronization point generally makes things simpler to implement and faster and just pretty much better in almost every way, provided that your sim is pretty quick so that most of your time is spent taking gradients and updating parameters. OK, so this is how you can have your online actor-critic algorithm with parallelism. All right, so now for the rest of today's lecture, we're going to shift gears a little bit, and we're going to talk about another way that we can use critics as a baseline in a policy gradient algorithm. So here, just for your reference, I have the equation for the actor-critic update that we've derived in this lecture. So this is your grad log pi times the advantage, and I've just written out the advantage here so you can see it. And then the alternative version that we covered last week is this one where you sum together the rewards and you subtract the baseline. So the advantage of the actor-critic approach is that it's lower variance, because the critic does a better job usually of approximating this expected reward, but it's not unbiased anymore. What that means is that in expectation, this way of computing your gradient might not actually give you the right gradient if your critic is not correct. And early on in the training process, your critic is probably not correct. Your critic is probably giving you values that are off in some systematic way. So no matter how many samples you average over to get this gradient, you won't actually get the right gradient because your critic is giving you nonsense. So this is not unbiased if the critic is not perfect. And in practice, this might manifest itself as your algorithm being less stable, meaning that it requires more parameter tuning to get it to work. The policy gradient version has no bias, which means that in expectation it is the true gradient, but you might need a pretty large number of samples to get to that expectation, which means that it has high variance. So can we use this v hat and still keep the estimator unbiased? So here's what we can do. What we can do is we can take our sum of rewards and we can subtract off a baseline that actually depends on the state. Now, why is this OK? If you remember my derivation for why the baseline is unbiased, The reason that the baseline is unbiased is because when you have this probability distribution out front, when you integrate over the thing that your distribution is over, which in this case is A, then this thing comes out to 0. The expectation of this thing comes out to 0. This doesn't depend on A. The distribution is over A. It's not over S. So that means that you can actually plug in any function of S in here, and it actually remains unbiased. This kind of estimator is going to have no bias, because this is just some function of S, and it's going to integrate out to 0. But it's going to have lower variance if the baseline is closer to the rewards. So the benefit here is that before we had a constant b, and now we have a baseline that depends on states. So if we have a baseline that depends on states, we can get these differences to be smaller. The quantity is smaller, because this thing can be closer to the total reward than some constant. So if these differences are smaller, then the overall variance of the estimator is smaller. So if v of s is closer to the expected sum of rewards than some constant, then we have a lower variance estimator. Now, the variance of this estimator is not going to be quite as low as this one, because we still have all this sum of rewards out here, but it's going to be better than this one. And in fact, you're going to implement a critic for homework 2, and because that homework is mainly on policy grading, you'll actually plug in your critic like this as a baseline. You can try the actual critic version too if you want a bonus question, but the thing that we'll ask you to do is actually just this. Well, and actually, since this will be on the homework, does anyone have any questions about it? Okay, good. So everyone will get that question right. Now, one natural next step that some of you might be wondering about is, well, we introduced a baseline. Let me just skip through this part. We introduced a baseline that depended on states. What if we introduce a baseline that also depends on actions, right? So this is the version that we discussed before. It has no bias, but you still have this sum of rewards. You get this difference to be even lower if you subtract a baseline that also depends on the action. In fact, if you have deterministic dynamics, you can probably actually drive this thing to 0 if your policy is almost deterministic. So if you can have your baseline also depend on the actions, these differences will be really, really tiny. So that seems like your variance will be even lower, which is completely true. The problem is that this is no longer correct. Once you have your baseline depending on the, let me just back up a little. Once you have your baseline depending on the action, now the expectation of this second term under your policy is not going to integrate to 0. So lower variance, but now incorrect. However, in some cases, you can actually fix this. So this is sometimes referred to as a control variant. And the idea is that this second term is going to introduce an additional correction. And that correction is this. It's the expectation of this second term. So you can subtract the term in here and add it back in here. Now, why the heck would you ever want to do this? Well, in some cases, depending on the form of Q, the expectation of Q under pi might be something that you can compute analytically. So, for example, if your policy pi is Gaussian and your Q is quadratic, expectations of quadratics under Gaussians can actually be computed analytically without taking samples. So you can subtract it over here from the sample by the samples, but then integrate it analytically over here. So here you're basically subtracting this little piece here where you have to use samples, which are going to be high variance, and then you're adding it back here, but what you're adding back in is the true expectation. So if you're lucky enough to be able to design a Q that can be integrated analytically under your policy, this can actually reduce your variance. If you have a discrete action space, very often you can do this, because with a discrete action space, doing this expectation under pi just means adding together all the possible actions. If you have continuous action space, a little harder, but there's still some ways to do this. So this is a way that you can use Q function critics without the bias. It's still unbiased, provided the second term can be evaluated analytically. And this thing we'll dig into a little bit more when we talk about variance reduction later in the course. And there's a paper by Gu et al. Called QProp that discusses a possible way of doing this. So takeaway from this slide is baselines that depend on state are unbiased. Baselines that also depend on the action are biased, but you can add a correction to make them unbiased, and sometimes you can choose the class of the baseline so that correction can be computed analytically. And this is called the control variant. Okay. The last topic I wanted to cover in today's lecture is going to actually combine critics the way that we've used them in the actor-critic algorithm, and critics as state-dependent baselines. So far we saw two ways to estimate advantages. We saw the sort of the critic approach, where you take your current reward plus gamma times the next value minus the current value, which this has lower variance and higher bias if the value is wrong, and the value is always wrong. And then we saw the Monte Carlo approach, where we add together the rewards and then subtract the current value. So this is the state-dependent baseline way of doing it. This has no bias, but higher variance because we still have this single sample estimate of the rewards here. So one thing that we might wonder about is, can we combine these two? So if we want to explicitly trade off bias and variance, we have something here that's low variance, something here that's low bias. If we want to trade off bias and variance, if we look at our performance of our algorithm and say, the bias is a little too much. Can I dial it back a little bit to kind of interpolate these two to lower the variance a bit, or to lower the bias a bit? It turns out that what you can actually do is you can blend between these two estimators. So if you want a little more control, if you run your algorithm and you find that it's too much variance or too much bias, you can adjust this little blending coefficient. So here's some of the intuition behind this. This is a plot where on the vertical axis you have the magnitude of the contribution of the reward to this single sample estimator, and on the horizontal axis you have time. And because we have a discount here, the contribution of each reward each time step sort of falls off exponentially. So the further forward in time you go, the less your reward influences your estimator for the A subscript MC case. But if you think about your variance, if your system is stochastic, you have all these possible futures coming from your single state here, and further in the future, there's more variance, because further in the future, this thing might have gone to lots and lots of different places. Closer to the present, the variance is smaller. So the contribution goes down, but the variance is going to go up. So at some point, you might say, well, if I go forward far enough, this single sample estimator, it's basically going to get drowned out in this massive sea of possible futures. So close to the present, it's giving me a good idea of what's going to happen. But very far into the future, there's just so many possibilities. So if I'm imagining, how my career is going to go 50 years in the future, if I just have a single point sample, I'm daydreaming in the afternoon and I imagine, I'm going to become an astronaut or something. Okay, that's one of possible futures. But there's so many possible futures that it's not really actionable at that point. So what I do is I draw the line. I cut here before the variance gets too big. Because past that point, that single sample estimator is just going to give me so little useful information because there's so many other possible futures that I'm better off using v hat, even if v hat is not that accurate. Because at least v hat is going to average together a few possible futures. So what I do is I cut. I say over here, I'm just going to cut off my rewards, and I'm going to put in my v hat. So I can write it out like this. I can say I'm going to add up the rewards from t prime equals t to t plus n. So this little boundary is going to happen n steps after the present. And then after n steps, I'm going to put in my value function. So I can do this, but this cuts off the future. I don't know what's going on here, so I'm going to add in my value function multiplied by gamma to the n. So this sort of fills in this little missing piece here with my function approximator. So this gives me, again, an estimator for my expected reward that uses this unbiased piece close to the present, but then puts this biased, but hopefully lower variance piece after some point in time. Now, at this point, I can already control bias variance trade-offs simply by changing n, right? So choosing n greater than 1 actually often works better in practice, especially in the early stages of training while v hat is not so great. This is sometimes referred to as n-step returns. So if you're interested in quickly and easily making your actor-critic algorithm better, raising n a little bit from 1 to maybe 4 or 5 might very quickly give you better performance, at least faster learning. Does anybody have any questions about this? OK. So there's another thing that we can do that's a little bit more sophisticated than simply controlling this integer-valued parameter. And that's called generalized advantage estimation. So generalized advantage estimation can be viewed as sort of a mixture of n-step returns. So do we have to choose just one n? What if we cut the returns everywhere all at once and then average them together? So this is our n-step return estimator. And what we can do is we can actually build a composite estimator that averages over all possible n's multiplied by some weight. And this weight now is a continuous parameter. And this weight basically controls how much we decay our returns to put in the function approximator. And this might seem a little silly, but you'll see kind of a neat connection to discount factors when I'm done with this derivation. So weighted average of all possible n-step returns. And how do you weight? Well, the intuition is that the returns closer to the present are more accurate, so if I become an astronaut 30 years in the future, that's not something that I can really guess right now. But what I'm going to have for lunch today, that's something that I can probably predict reasonably well. So I'm going to prefer cutting earlier. So I'm going to prefer to keep the sum of rewards earlier, and then prefer to put in the value function later. So one reasonable way to set these weights is to set them to be on an exponential schedule, just like the discount factor. So I'm going to set the weights to be lambda to the power of n minus 1. Proportional to that. So the weights have to sum to 1, obviously, so I'll set them proportional to this and then normalize. So that means that the bigger the n is, the less I'm going to consider that estimator. So it's an exponential fall off. And then I can, yeah, sorry about the scary equation, but then what this ends up being is it's a kind of linear interpolation. So every time step, what I do is I linearly interpolate between v hat and the next estimator. So if lambda were to be set to 1, then I would cut right away. So that would mean that, to 0. If it was set to 0, then I would cut right away. I put v hat on the second time step and ignore the second piece. But if lambda is somewhere in between, then I have sort of a weighted blend. I'm going to blend at the first step by 1 minus lambda and lambda. At the second step, it's going to be also 1 minus lambda and lambda, but this thing has lambda in front of it, so then it's going to be like lambda squared. So it's every step, it's a weighted blend of v hat and the future estimator. Going through some of the math for this, which I won't go through on this slide, we can actually reduce this GAE estimator, this estimator that blends together different n-step returns, into a very simple form, where at every time step, you take this delta, which I'll define in a second, and you multiply by gamma times lambda to the t prime minus t. And what is delta? Delta is just the actor-critic style estimator at time step t prime. So it's just a bunch of algebra, but you can actually go from this equation to this very simple equation where at every time step you're just doing gamma times lambda to the t prime minus t times the actor-critic style estimator at step t prime. And this simplification of the GAE estimator actually sheds some light on the role of discount factors, a role that's very different from this sort of life or death version that I introduced before. Lambda acts very similarly to a discount over here. And lambda, if you remember, is the parameter that controls bias variance trade-offs. So if lambda is small, then we're going to cut off early, which means we're going to have more bias but less variance. If lambda is big, we're going to cut off later, which means less bias, more variance. So in the same way that lambda controls bias variance, so does gamma. Gamma gives us more biased estimates because we really want full infinite horizon, but it lowers the variance because we're cutting off those really weird long-term predictions because single sample predictions years into the future are just not that useful. So we're basically stopping ourselves from imagining that we're going to become an astronaut 20 years from now for the sake of having a more reasonable expectation about what we should do today. So if you remember this option 1 when we discussed discounts, discount is just acting as a variance reduction trick. So this is an alternative interpretation of discount factors as a way to control bias variance trade-offs. Okay, does anybody have any questions about this? All right. So to review what we covered today, and I'm going to review and then I'll show some examples, so don't get up and leave yet. There'll be some cool videos. So to review, we talked about actor-critic algorithms. We talked about how the actor is the policy, the critic is the value function, and introducing the critic reduces the variance of the policy gradient. We talked about policy evaluation, which is the process of fitting the critic. We talked about discount factors, how there's like this you have to collect your rewards early interpretation, but there's also this other interpretation that it's a kind of a variance reduction trick. And both of these are valid ways of looking at discount factors. We talked about how we can design actor-critic algorithms. For example, we can have one network with 2 heads, and that gives us a bit better efficiency, but is maybe a little tougher to set up. We talked about batch mode or online algorithms, and for online algorithms, you might consider parallelizing them to have larger batches. And then we talked about state-dependent baselines, which is another way to use your critic. And then how we can combine n-step returns, which is Monte Carlo plus bootstrapped estimator, and we can actually blend multiple n-step returns into the generalized advantage estimator. All right, let's look at some examples. This video is showing a little humanoid learning to run. I think I might have showed this in an earlier lecture too. This is from a paper called High-Dimensional Continuous Control with Generalized Advantage Estimation. This is a batch mode actor-critic algorithm. And this batch mode actor-critic algorithm is blending Monte Carlo and function approximator estimated using that GAE thing, using the blend of n-step returns. So this is an example of that in action, and it eventually learns to run. Here's another video. This is a paper called Asynchronous Methods for Deep Reinforcement Learning. And this paper proposes an online parallelized actor-critic algorithm, and this is the one that is not synchronized, so it's actually asynchronous and parallel. Here, they're actually also using n-step returns with n equals 4. So they actually sum together the rewards for 4 steps, and then they put in their critic. And that gets them somewhat faster learning. And they have a single network for both the actor and the critic. So they have one network with 2 heads, because they're doing this from images, so they want to share those visual features in the network. And here this is a video of their learner navigating a maze and picking up apples, which is a good thing for reinforcement learning to do. Some suggested readings if you want to dig more into some of these topics. This is a classic paper by Richard Sutton and colleagues, which introduces actually a few things. It introduces the temporally decomposed estimator that we discussed last week, and it also talks about actor-critic algorithms with value function approximation. So if you're interested in reading a classic paper on this, this is a good one to check out. Some more recent deep reinforcement learning papers. This is the asynchronous paper that I showed on the previous slide. This is the paper with the little guy running to walk. And then this is the paper that uses control variates, which are baselines that depend on the action. And this is something that we'll also discuss potentially later on in the course. All right, that's it. See you all on Wednesday to discuss Q-learning and value function estimation.